Hi, today we'll talk about the proofs, and we'll particularly illustrate the idea of how do we make proofs in predicate calculus using integers and some basic notions about integers. So first definition, we want to have, in order to write a proof, we have to have precise definitions. Otherwise, we cannot manipulate some verbal statements. So we need to usually have formulas, usually equalities, inequalities, so some mathematical objects that we can manipulate in a rigorous way. So generally what? So definition, n is even. So that's more verbal, and here in the definition we'll precisely using mathematical formulas of predicate calculus, describe what do we mean when we say that n is even. So n is even if there exists k from z such that n equals 2k. So whenever we see this expression, we'll actually think of this equality. N is odd will always be treated there exists k from z such that n equals 2k plus 1. So once again, this is verbal and this is formal. And whenever we see a statement involving one of these verbals, we always want to trade it for something that's formal. And the other definition, I will skip a few things from my notes that are just self-explanatory, by the way, or maybe I should. So, example, so 17 is odd. Why? Because, actually, I can find the witness. So, because 17 equals 2 times 8 plus 1. So I found the witness, I found the k, so k equals 8, such that 17 equals 2k plus 1. And 14 is even, because 14 equals 2 times 7, where my k is now 7. And of course, natural question here is question. Can a number at the same time be even and odd? So that's a natural question. And let's see how are we going to prove that that will never happen. So the answer is no. And here's the proof. So, assume that a number, an integer n, is both even and odd. So the fact that n is even, according to definition, I can translate and say, oh, that means that n equals 2k for some k in z, for some integer k. But also, since n is odd, we can say, all right, n is also equal. Now comes the typical error. Very often people say 2k plus 1 for some k z. This is the wrong way to say it. Why? Because each of those two statements has its own witness, and no one says that that witness has to be the same. Once you call it K, you're actually claiming that there's the same weakness, and nobody said that, so you cannot assume something that's not there. So generally, in order to avoid that special assumption which is not valid, I will not call it K, I will give it a different name, I'll call it L. And why this cannot happen? Because here it is, I will compare these two lines and I'll get the following. If n is equal to 2k and n equals 12 plus 1, that would give me that 2k equals 12 plus 1. Then getting those even numbers on the left side, I will get 2 times k minus l equals 1. You see what happened? Here I had some statements that are hard to manipulate. You are never sure what you are concluding from there. Now we have equalities, which are our important machinery that we studied, developed, and generally we are on much more solid ground trying to reach some contradiction here. Why is this not possible? Because we can say the following, we can say the following, which cannot happen. I'm actually here arguing by contradiction, and in section 2.5 we'll talk more about that type of proofs, which cannot happen because k minus l, if it is an integer, we have two cases. Case 1, if k minus l as integer is greater than or equal 1, then 2 times k minus l is greater than or equal to 2, so it cannot be 1, it's too big. But then, case 2, if number is, because you know how numbers go, 0, 1, 2, 3, 4, negative 1, negative 2. So if you are not greater than or equal 1, you are in the second territory, less than or equal 0. So you are there then. That's a blue version, and this was the red version. Now you are in the blue territory, so that means that k minus l is less than or equal 0, but then 2 times k minus l would be also less than or equal 0, so it cannot be 1. So that 2 times k minus l in red, because when you double it, actually what happens, that gap becomes bigger, because blue guys, when you double them, they give you a result that's 0 or below. Let's say blue. And the red guys gives you 2 or above. So nobody will hit. Oops, I need third color. Nobody will hit my number 1. Here is number 1. And that's why the same number cannot be, same integer cannot be at the same time even and odd. What else? In this section we also wanted to start talking a little bit more about prime numbers and composite numbers. So, and here is the definition. That notion is reserved for positive integers, and not only positive integers, one is excluded from that story, and you can see that from definition. So definition, let n be a positive integer greater than 1. So 1 is not in the game here. So what? We say that n is a prime if the only factors of n are that trivial factorization. And then the same way we say that n is composite if, and then I'll quickly say if it has other factors, or I say if it has also a non-trivial factorization. So for example, 7 is a prime. Why? Because the only factorization of 7 is 1 times 7. But for example, 10 is composite. Because 10 equals 1 times 10, but besides the trivial, it also has, let's say, 2 times 5. So that's why that number is composite. All right, and then knowing these two definitions, we can now again illustrate a few statements that we prove about prime and composite numbers. So that's example 232. I'll try to squeeze it in here. Example 232. And the question is, prove or disprove that there exists n from z such that 2n squared minus 13n minus 7 is a prime. So generally, if you look at the logical structure of this statement, it's an existential statement. So we need to provide a witness. How do we find that witness? Maybe we can start, from 0 and go and hope that once we'll run into a witness, but it might be that that witness is far and we'll never reach it, or maybe it doesn't exist, so we'll never know. So we'd like a little more organized search. So generally, this problem gives us a chance to solve it because this expression has some special structure. Why? Because let's look at the expression, even if we don't know a solution, even if we don't know what n is, this quadratic expression has a nice and easy factorization. What would that factorization be? N minus 7 times 2n plus 1. Of course, you can ask, how do we know that there's a factorization? For example, there are also some methods from intermediate algebra. How do you factor quadratic expressions? For me, the simplest one is just solve quadratic equation and use factorization theorem. So generally, 2n squared minus 13n minus 7 equals 0. If you solve quadratic equation, you get 13 plus or minus square root of 169 plus 56 over 4, which will be 13 plus or minus 15 over 4, which would be 28 over 4, which is 7, or negative 1/2. And then this factors out as 2 times n minus 7 times n plus 1/2. Factorization theorem says if you have a 0, you have n minus that 0 factor and the other one, and 2 is the leading coefficient. And then if you multiply by 2 here, you see with that 2 on the second factor, you exactly get this. Anyway, this is less important than the algebraic part, but probably you are curious, how did we know to do that? So let me exclude that. So question is what? So most of the numbers will be composite in this, most numbers in this form will be composites. Why? Because here is a factorization. And the only way to make this prime is to force one of these two numbers to be 1. So in order, and that might not help, But if you don't force any of them to be 1, then here's your non-trivial factorization and your number is composite. So let us try to force one of the factors to be 1. So who could be 1? So either n minus 7 should be 1, or 2n plus 1 should be 1. This one will not give us anything. Why? Because it's very easy to see that when 2n plus 1 is 1, then n would be 0, then n minus 7 would be negative, and then negative number is not a prime according to our definition, so that will not work. So basically what it tells you is that our only hope is n equals 8. So if n equals 8, why am I saying it's only our hope? Because yes, you made this factor 1, but nothing guarantees that the second one might not be on its own composite number. So we'll see. But what we wanted to say is nothing else but 8 would work, because whatever else you try, you will get either negative number or you will get something that has non-trivial factorization. So let's see what happens when n equals 8. When n equals 8, we'll get what? 2n squared minus 13n minus 17 equals 1 times 17, which is 17, which is a prime. So here it is. So we actually found our witness. So the answer is yes. A witness is n equals 8, and the statement is true. So if it's existential statement, then one of the straightforward proofs is just to find in the witness, but as I said, you should do your search in an organized way and not like, going number by number, because that might not give you any good results. All right, let's see something else. So in part 231, we talked in general about the proofs of universal statements. So if you have proof, to make a proof of universal statement, then you actually need to provide the proof for arbitrary object. So let me see, 2.3.1, universal statement. So in that case, let me consider one example. For all integers n, for all even integers n, or for every even integer n, n minus 6 over 2 is also even. So what? It's a question here that is this statement true or not? So generally we have two options, either to prove or disprove. If we were to prove it, then we need to start from an arbitrary number. So you cannot just say, let n be 8, or n, because it says for all even integers. That's why this is universal statements, proofs of universal statements. Generally, you need to start. So prove, if you want to prove it, then we want to prove it for an arbitrary by fixed, arbitrary but fixed number, even number. So generally, we need to start with the assumption that our number, so let n be even. And then what does that mean? That n equals 2k. And from there, I want to show that the number n minus 6 over 2 is 0. Let me try it. I go 2k minus 6 over 2, because that's n minus 6 over 2. And that is, with a little algebra, factor out 2 and cancel, you get k minus 3. Now I'm a little bit worried. Why? Because there's nothing that tells me that this number is even, because there's nothing forcing this to be even. So now I say, maybe this statement is not true. So what then? So if you get stuck, what can happen? If it will happen that just we didn't come up with a good idea, or maybe the statement is really not true. So generally what I will do, I will test it and try to find a counterexample, so-called. Try to find counterexamples. Find just one. So you see, to prove it, you need to prove it for all. To disprove it, you just need to find one counterexample. And for example, let me do n equals 8. What do I get? N minus 6 over 2 equals 8 minus 6 over 2, which is 1, not even. So what is it? We actually disproved this statement and showed that from the fact that n is even, we cannot prove that n minus 6 over 2 is even. Here's your counterexample. So not true. So generally, once again, you either need to prove it for arbitrary number, and we'll do a couple of those where that works. Here we actually showed it with a counterexample. Here's another example, again, for a universal statement. Example 237. It says the difference of an odd integer and an even integer is an odd integer. Proof. By the way, it's also a good exercise here to record this formally. That's basically what we'll discuss mostly in 2.1. So you see, when you are trying to formalize a statement, here is one of the most important things, to introduce variables. As I said, we don't have to write formal version, but I think it's a good exercise. So this statement is about two numbers, because of an odd integer is one of them, and an even integer is the other one. So we introduce a variable for each of them. So x will be variable for the odd one. Y will be the variable for the even one. So what then? The difference of an odd integer and an even integer. So we say the following. For every x and for every y. So we are just making the statement for any two objects. It's all in integers. So now what? What do we know about x? It says we know that x is not arbitrary. X is the odd one. So we say O of x. What else do we know? We know that y is even, so we know even of y. And then what? We want to prove that their difference is odd. This is what we really said here. So what we said here and what we said here is exactly the same. Be careful, I already mentioned that in section 1, but it's never too much to say that. You have to be very careful about parentheses here, because since I have completely outside parentheses, what it says is, whatever x and y, if this true, this will be true. Just for a moment, let me change this and make this one here. Just by placing parentheses there, then what am I saying? This statement stands on its own. And that statement is false on its own. Why? Because what this one says is that for every two integers, one of them is, first of one has to be odd, and the second one has to be even, which is not true. If I choose x to be 6, this is false. False follows everything. This is true always. That's not what it says. It doesn't say that this assumption is always true, but it says whenever this is true, this has to follow. So be careful. That's really, graphically it looks almost the same thing, but meaning-wise it's completely different. Anyway, how do we prove that? We say the following. For every x, and so pick arbitrary x. X. And pick arbitrary y. And then what do we assume about them? We assume that it's not really arbitrary. We know that it's O of x is assume O of x and assume E of y. Okay, so those are our assumptions. And then what? The only thing is we want to get that x minus y is odd. And actually, I always like here in these settings to talk about crossing the river. So here are the statements. So here is left side, here is right side, this is the verbal end. And here is the formula end. And you want to go from left side to right side here. This is your verbal statement. So what do? And formally has a bridge, and that's your knowledge of mathematics and formulas. So what you do, you go verbal into formulas. That's what we learned today. Then you cross the river in the formula land, and then you go back from formulas to verbal statement. So that's what we did here. So here it is. O of x is verbal. Now I'll cross to formulas and I say, what does it mean? That means that x equals 2k plus 1. Now I'm in formulas. So this is now formula land. Even of y says y equals 2l. It's also in formula land. Look now, I have equations that I can manipulate much better and safer than the sentences. Oh, of course, I didn't say here for some k and z, and for some l. All right, so generally, now the question is, we are among the formulas, how do we cross, knowing what x and y are equal, to what is x minus y equal, because that's what the story is about on the right side. And then what? Just using formulas, it's very easy. X minus 1 is 2k plus 1 minus 2l. And exactly, this is the moment where I cross the river. So this is the story about x minus y in the formula land. But now is the question, can I cross back into verbal land? So can I, from this formula, somehow conclude that x minus 1 is odd? It should be fairly simple. Those two, if you factor out 2, k minus l plus 1. Now let's call k minus l, let me call it s, which is also integer, because difference of two integers is integers. So this looks like 2s plus 1. So what did just happen? That actually we wrote x minus 1 in the form 2s plus 1, and we had the witness to say, oh, so x minus y is odd. Why? Because of the definition of odd numbers, this is the moment where we cross from the formula land into verbal land. And that's how it always goes. From verbal to formula, manipulate formulas using your knowledge of algebra, and then back to verbal. And it's good maybe to be aware of this diagram so that you follow your procedure all the time. So that's the proof. Since we did it for arbitrary x and y, we have a full formal proof. All right. And then let me talk a little bit. One of the examples here is about showing that the square of odd number is odd number, works the same way, so I think now it would make more sense. Also, division in the cases. So what would that be? Well, let's do one of the examples. Again, I'll talk about it. Division into cases. So I'll do example and then I'll formalize the principle, and that is example 2, 3, 11. It says the square of any odd integer has the form 8m plus 1 for some integer m. I'll go a little faster here, generally without all these additional writings. But the proof goes the same way. So it says the square of any odd integer. So x, arbitrary odd integer. Now I wanted this verbal object to transfer into equation, and that is x equals 2k plus 1 for some k z. Alright, now I want to make conclusions about the square, so that's manipulation using formulas. So now we know that x squared equals 2k plus 1 and then squared. So now I'm trying to cross the river again. So this is formal and this is verbal about x, but now I want statement about x squared. I'm just crossing the river through that. So formal about x, this is formal about x squared. And then I use little algebra, so that's 4k squared plus 4k plus 1. All right, I look what I need on the right side, just to guide me. So that plus 1 I like, I have it, I keep it. But I'm not sure why would this be equal to 8 times something. I can factor out 4, but I need 2 more. So it says k squared plus k plus 1. So basically I need somehow to show that this number is even. So if I can factor another 2. But that's not so obvious as a minute ago, but here it is. I do 2 cases, and I need to prove that no matter which case appears, that the statement will be true. So in each case I have to prove what I need to get 8m plus 1. So case 1, k is even. Case 2, k is odd. And there is no third case, so generally these cases need always to exhaust all the options. So these are the only 2 cases, there's no third case. And then what do? when k is even, why would our number be even? Then just again, k is even, that means that k is some number 2l's. So our x squared will be 4 times 4l squared, I plug it in, plus 2l plus 1. I can factor another 2 and get 8 times 2l squared plus l plus 1, which is 8m plus 1, where m is obviously 2l squared plus l. So this is checked. That's good. If k is odd, the same thing, just a little different algebra. I need to close with, say, that case as well. So when we plug it in, k squared would be 4 from outside. Then that k squared plus k would be 4l squared plus 4l plus 1 plus 2l. A little heavier algebra, but nothing bad. Plus 1. Again, because 1 and 1 is 2, I can obviously factor out 2 again, and I get the little algebra 8 times 2l squared plus 3l plus 1 plus 1. I think I'm correct about that, rushing. So if I call this m, and that's an integer, I have 8m plus 1. That's checked. So once again, just verbally saying, if you have exhaustive cases, so that there's no third or fourth case, or there are no other cases except those that you analyzed, and if you prove the statement in each case individually, then you have the full proof. And that's the statement that we actually expressed. If we have what? I'll just write it a little different than in the notes, but that's also correct. If you show that A1 implies B, that's your first case. You show A2 implies B, and as many cases as you want, that each of them implies B, but also you show that they are exhaustive. That means that one of them has to show up. Then that's the same as you prove B. And that's exactly what we applied here, just on 2 cases. First assumption implies B. Second assumption, one of them must appear. B is true itself. And then at the end of this section, we want to just illustrate some of these statements. Methodology of proofs on rational numbers. So generally rational numbers are defined. So what is a rational number's definition? A rational number, so Q is a rational number if Q is basically fraction, m over n, where m and n are both integers. And what else is very important? That n is not 0. Sometimes we also say that n is positive on its own, but generally we'll just say n is not 0. So if you can find those witnesses m and n so that you write your number as a fraction, then you are saying that q is a rational number. And then what? We have operations about these rational numbers. So how do we define operations? If you have m over n, let's say, I better use the same letters as in the notes. K over L. By definition, this is not proof, you just cross multiply as you know, ML plus KM. And then it's important that since these two numbers are both different from 0, and L is also different from 0, so you don't need to worry about it, if N and L on its own are different. Then you define how you multiply two numbers. And there are the and subtract, and how do you divide it, and so on. And then here we mentioned one very important principle here that you used in algebra, and this is called zero product principle. That's about integers here, and that's the one that I called here. If those two individually are not zero, and L is not also not zero, so I wanted here to emphasize that important theorem about integers. It's called zero product principle. Maybe it's better to use the black marker. Zero product principle says, so for m and n in integers, if product of two integers is zero, then one of them must be zero. And that's principle that you use all the time in algebra when you solve equations, this or that, but just it's good to have it here explicitly stated if you forgot it or you never saw it before, because this is a very important principle for mathematics, and that's exactly what we used here. If this denominator is correct, not zero, and this denominator is correct, then this one is also correct. Actually, the way I called it, I said the following: n different from zero and L different from zero imply that n L is different from zero. If you compare those two, I hope by now you already recognize that they are the same thing. This is basically contraposition. Because we took negation of the consequence and used them organ, so they become negated and or became n, and these guys just negated and we reversed them. So generally, this zero product principle is very often used both ways. And for example, I just showed you here, how do we show that A plus B, so for example, prove, for example. Prove that for every two rational numbers, A plus B equals B plus A. That's commutative law for rational numbers, and you are already familiar with that law. You've been using it during your algebra. Here we want to see, can we prove that property using the definition that we had? And generally, here's what you do. A plus B, please prove. So if A and B are rational by definition, that means they are both fractions. So let's say A is m over n, and B is k over L, and n and L are different from zero. And then how much is A plus B by definition? Definition says cross multiply and add them up, so it would be ml plus kn over nl. I'm doing it exactly the way they are written. I'm not reordering them or anything. I'm doing it the way computers do it. So they just read, scan, and they plug it in, and they don't have any knowledge on that. So what about B plus A? Now, that's now K over L first, plus M over N. When I cross multiply, I get Kn plus, how does the definition say who comes first up? So plus ml over L. So I open the both things according to definition, and my question is, are these two things equal? And the answer is yes, they are equal. Let's squeeze in here the last sentence. They are equal because NL equals Ln. Why that? Because this is commutative law for integers. And the same way, ML plus Kn the same as Kn plus Ml. Again, commutative law for integers and multiplication. This is commutative law for integers and addition. So since numerators are equal, denominators are equal, according to equality definition between two rational numbers, they are equal. So basically all these problems that you have in the homework and that might appear on the exam, whenever a statement says, prove that for rational numbers, then you immediately write them as fractions, call the definition, and then see, using properties of integers, how could you make a conclusion about your rational numbers. That's first observation. The second one is, or let me give you one more example. So just how do you disprove something about rational numbers? You can find that in your homework list. For example, someone says, example, prove or disprove that if I have two rational m over n plus k over l equals m plus k over n plus l. So prove or disprove. So generally what? This is what we see very often in very low level algebra classes, where people make this error and they add up fractions, just adding numerators, adding denominators, and then you want to tell them that actually that's not a valid law of algebra, that they cannot apply that law. So basically, you cannot prove it because this is not correct. What we want to hear is to disprove it. Because basically, even if you don't say, this means for every m, n, k, l, when there's a law, you are assuming always universal version of the law. So this is what someone who thinks that this is a good law would think, that whenever I have two fractions, no matter who's up and down, I can just add numerators and denominators. How are we gonna disprove that? Then we'll just choose. So find the counterexample. So let's say 2 over 1 plus 1 over 2, and I'll ask, is that equal to 3 over 3? Because when you add, you get 3 over 3. Obviously, on the left side, we get 2.5 or 2.5, and on the right side, we get 1. Obviously, this is not true. This is false. So that shows that a rule is not valid, that's not how rational numbers or fractions behave, and that's what it is. So to disprove a law, so-called law, you just find a counterexample where that rule doesn't work. The same way, for example, when you want to convince someone, it's not about rational numbers. Example, when people say a plus b squared equals a squared plus b squared, is that a valid law? Then you just take an example and say a equals 1, b equals 1. When you plug it in, you get 1 plus 1 squared equals 1 squared plus 1 squared. 1 and 1 is 2, squared is 4, equals 1 and 1 is 2. Obviously, this is not true, this is not true. And you provide a counterexample that this is not a valid law of algebra, and this is again counterexample. It's false. That was it. Thank you.